Off with probability, scale from 0 to 1. Of course, 1 is certain, 100% chance. 0 is 0 chance. We're going to express probability as fractions, as decimal numbers, as percentages. So it's a number from 0 to 1. And let's say an event is some observable outcome. The sample space, which is eta, remember that one? Yes, all possible outcomes. We've got the probability, and this is our fundamental rule for probability. The number of outcomes we observe divided by the total number of outcomes in the sample space. All right, so we're going to use some notation here to denote our events. So let's consider rolling 2 dice. Okay, so let's have 1 dice come first in a ordered pair, and the second dice, the outcome, could come second in an ordered pair. So we could have 1 1, 1 2, 1 3, 1 4. How many different outcomes do you think there are all together in this sample space? Total different outcomes in rolling 2 dice. It's not 12. 6 plus 6 on a dice gives you 12. No, we're going to have 36 different outcomes. For every 1 on a dice, we've got 6 on the other dice. 6 groups of 6 is your 36. Let's consider 2 events. Rolling 2 dice whose sum is an even number. So we're talking about 2 numbers adding together to give you an even number, like 2, 4, 6, 8, 10. And then we could also consider a second event, rolling 2 dice whose sum is a number greater than 8. Such as I roll 2 dice and I get a 4 and a 5, whose sum is 9, an outcome greater than 8. Okay? Now, let's look at all the numbers of outcomes in A. There they are. We get 18 of them all together. We keep writing them. Another one could be where the sum is even. I could have a 3 with a 3. Okay? Both 3s, and they're 3 plus 3 is 6, which is an even number. Oh, and now what about the number of outcomes in event B? I'm going to have 10 in total, and there they all are, listed as ordered pairs. So you can ask yourself, well, what's the probability of rolling 2 dice whose sum is an even number? Well, I'm thinking about the probability of event A, which is the number of outcomes in A, 18, over the number of outcomes in the sample space, 36. 0.5 or half. Okay? Simple ratio of numbers we are forming when we're evaluating probabilities. Okay, so far so good. Let's look at some composite events. We have a complement of an event, which we're going to denote as A dash, and the type of wording we were looking for is not an event, such as not rolling an even number. It is not raining tomorrow. Kai will not stay up till midnight doing work. Cameron will not keep working all night. Everyone will not forget to do their homework this weekend. Union of 2 events. Event A or event B. Okay? The intersection of 2 events is event A and event B occurring together, same time occurring. Okay? And it could even happen 2 events one after the other, such as I flip a coin, then I roll a dice. And what's the probability of flipping a head and rolling a 6? Now, we like to have our Venn diagram to help us think about things, because here, the green section right there is what we call our intersect. A intersect B, the region that pertains to both A and B. We have a rules, some probabilities of working out each of these types of composite events. So here's the 1 minus probability of A gives us the complement of A. We have the union, probability of the union of two events. So that is, we take all of A and then we add all of B. But by adding them two together, we've doubled up twice parts of the intercept. So we have to subtract one of them. Okay? We call that the addition rule of probability. And it can also be thought about in terms of counting outcomes. So if I add up all the outcomes of A or B occurring, then divide by the sample space, I get the same value for the probability. It's important to think about, to be able to think about both ways of doing it. Now, probability of the intersect, A and B occurring together, is multiplication rule, where we have this expression. This is probability of B given that A has occurred. This is a conditional probability statement. Given that is the wording we use to represent that bar. So probability of B given that A has occurred, multiplied by the probability of A. In this formula, it's always good to remember what comes here in the second factor when we multiply, in the multiplication rule. It's always the probability of the event that's given. So if that's given A, I always multiply by the probability of what's given. Probability of what's given, as in given event A has occurred. Now we can see it's also equivalent to this form here, where we can swap the order in which the events occur. Probability of A given B has occurred times probability of what's given, probability of B. Now, fundamental rules. We have multiplication rule of probability, addition rule of probability. We've got complement of probability, okay, and our different ways in which we talk about our events. So, let's put it to some practice. Let's come back to our dice experiment. What's the probability of rolling two dice whose sum is not an even number? Okay, so I have to use my complement rule. Probability of not an even number is 1 minus probability of an even number. So 1 minus 18 over 36 is 50%. Okay, so far so good. What is the probability of rolling two dice whose sum is not an even number or a number greater than 8? So looking at the keywords there, that's the complement of event A, or corresponds to the union of two events. And then I've got my two events in description form here. And it's important to be able to read a probability question and identify what is the event that's occurred, and we're defining the events, such as here. Number greater than 8, well, that's event B. And then whose sum is not an even number, that's event A. So I'm going to use what kind of rule to work out the union of those two events? That's this one here, that's my addition rule. Let's employ that one. So I've got probability of not A, union of B is the probability of not A plus the probability of B minus probability of not A intersect B. Now, we don't know anything about this as yet. So let's have a little look what we get. Just down here, and we'll have a look at both sections. Now, I don't know much about this, but what I'm going to do is count it up. I'm going to count by thinking about the problem in a logical way, all the outcomes that occur for A not intersect B, when it is not an even number and a number greater than 8 at the same time. So what are all the odd numbers greater than 8? 3 and 6 sum together to give 9, but I could also have 6 and 3. Yeah, 2 dice, remember, 9. And then, what's another number greater than 8? Well, it's still 9 because I can also make 9, 5 and 4. That's sum to give you 9, which is odd. 4 and 5 sum to give you 9, which is odd. And then what's the next odd number? 11. 5 and 6, and 6 and 5, they sum to give 11. And that's all the numbers greater than 8 that I can roll on 2 dice. So I've got 6 of them there. Okay, and I found it by what's called inspection, inspecting all the outcomes for an event. So here I go. I've got 6 out of a possible 36 for the intersection. I've got 18 out of 36 for not A and 10 out of 36 for probability of B. And put it into sum and I get my 11 out of 18, 61%. Okay? Let's look at one more. What is the probability of rolling 2 dice whose sum is an even number or an odd number? Even number or an odd number. Well, numbers can either be even or odd. So, what's the being, again, an or problem? We're going to use the addition rule. So I see that A or not A is the probability of A plus probability of not A minus the intersection between the two. Hang on. That looks rather familiar. If I just hide the intersection and I think about that, what does that equal to? Very good, Ifa. It's 1. Alright. And why is the intersection 0? Well, it's because we call A and not A, they're mutually exclusive events, meaning that they cannot occur at the same time. We can't have day and night occurring at the same time because they're mutually exclusive events. We can't have an even number and an odd number occur at the same time because they're mutually exclusive events. So the probability of that happening is 0. So a fundamental definition here. Mutually exclusive events, they're disjoint, meaning apart. There's no overlap, no intersection. It's an empty set, a null set. And so the probability of a null set is 0. And on the Venn diagram, we have disjoint sets separated in that manner. Okay? So an example is rolling an even number and a 1 on a dice. Well, because 1 is an odd number. Now, another important thing that's worth thinking about is this idea of an independent event. What is an independent event? Consider it as the probability of one event does not depend on the occurrence of another. So that means that the conditional part, probability of A given B, if A doesn't depend on B, then it stands alone. This is true. And then our multiplication rule becomes this for independent events. Okay, if what's given is equal to just probability of A, then probability of A times probability of B. They multiply straightforward in a straightforward manner. Rolling a double 3 on 2 dice. So that means rolling a 3 on one dice and then rolling a 3 on another dice, a double 3. Okay. Now, the probability of rolling a 3 on one dice doesn't change the outcome of rolling a 3 on a second dice. They are independent events. So each is 1 out of 6 chance of rolling a 3. So being independent events, I use multiplication rule because I'm interested in them happening together. And is the key word there. So we use the intersection. We get 1 out of 36. Alright? Rolling a 3 on a die, on one die, doesn't affect the probability of rolling a 3 on the other die. It's a very important thing to be able to recognize our independent events. But we can't always easily identify independent events because there's a difference between physical and mathematical independence. So I gave an example of a physical independence, and another one is if I roll a die and draw a card. They're two separate events. They don't interact with each other. So the chances of the probabilities of getting outcomes in drawing cards is completely independent from the probabilities of getting outcomes in rolling a die. So that's an example of a physically independent event. But there's a larger scope, larger ways in which we can think about that. And it's the realm of the mathematical independence. And we can see all possibilities of physical independence is a subset of all possibilities of mathematical independence. So what is mathematical independence? Consider this definition. Since the probability of B given A is equal to probability of B, then that means we get this via the definition and using multiplication rule. Now I'm going to break that down a little bit to come up for a little test to find mathematically independent events. So let's use the definition of probability, where I have the number of outcomes divided number of outcomes in the sample space. I'm going to clean it up a little bit. I'm going multiplying both sides by n of eta, the number of outcomes in the sample space, and I get this little expression here. Okay, and it's basically saying, well, both of them together, A and B, if I can add up all those outcomes, okay, then it's equivalent to this right-hand side. Let's see how this works, putting it together. This is an exam problem. This pops up now and then. So, sample space when a fair die is rolled is 1 to 6, 1 0, 5, 6, with each outcome being equally likely. Probability of each is a sixth. For which of the following pairs of events are events independent? So there's nothing about the physical nature of these events, so we have to draw on some mathematical independence idea. And we had a test saying A intersect B is equal to the number in A times the number in event B over number in the sample space. Okay, now we want to go through it and think about some of these trial by error. Now, the number of outcomes in A and B, for each I want to think about A and the second one B. And is where they are both the same. The outcomes are the same in each event. So what I can do is start finding, come over here, Mr. Rule, thank you. I'm going to find the intersect of each one. So little column here, A intersect B, where they are the same. So I'll have 1 and 1, yep, they're the same, and 2 and 2, they're the same. So my intersect is 1, 2. Okay, for the next two events, I've got 1, 2, 3, 4. Well, there's no outcomes, they're the same, so it's null set, empty. So I'm going to cross that one off already, just in anticipation. It just seems to not be correct at all. Now, what's the intersection in these two events, A and B? Let's have, that one and that one are the same there, so I've got 1 as the intersection between those two. That one, and again 1. It's the intersection between those two. Outcome 2. Alright, so applying the rule, each of these is, there's 2, there's 0, there's 1, 1, and 1 element. Mr. Rule, I'm going to get you to come over here again. No, Mr. Rule. Oh dear me, we're going to crash into stuff. Isn't it great when you try and do things freelance and it just doesn't work out? Okay, so I sorted out Mr. Rule and we're going to continue on with our work here. So of applying my little test rule to each example, we've got the number of outcomes in the intersect on the left hand side. Let's get the right hand side going. So number of outcomes in A times number of outcomes in B divide number of outcomes in the sample space. So we come over here, we've got 3 and 2, 3 times 2 over the number in sample space, and we've got 6 of them, 6. Okay, now 2 doesn't equal to 1, 6 on 6 is 1, so that's not correct. And then the next one, I've got 2 and 2, 2 times 2 over 6, again that's not correct. Now here I've got 3 and 3, 3 times 3 over 6 is not correct. Oh, get the idea? What about the last one? We've got 2 times 3, 2 times 3 over 6. Oh yes, ding ding ding, we have a winner. Okay, so we have these two events, this one and this one. They are independent events. And we don't know anything about their physical nature, so we use an idea of that about mathematical independence using our little rule here. Hi. Okay. Okay. Now, another important thing with probability are these graphical representations, and we're going to go over 3, the Venn diagram, tree diagram, and a Karnaugh chart. Now let's have a look at Mr. Venn. We've got a few regions that are worth noting. We've got this region here, we've got that one there, this one and this one. Now it kind of covers all possibilities, all 4 ways in which the whole sample space can be made up. Okay? So first off, the yellow, the big circle here of event A, it's made up of Mr. Yellow Pac-Man and his green lunch. So A, being event A, the whole circle, is this event, A intersect B naught, union with, together, joined together, A intersect B. Now, if I'm interested in the probability of A, it is about using my addition rule of probability, because I've got 2 events that I'm taking the union of. Same way of approaching with what we have over here in event B. Mr. Blue Pac-Man is eating his green lunch, his vegetables, and we have A naught intersect B, union with the A intersect B in the little green bit. Now, let's think about how those two go together. The union of 2 events is given by our addition rule, so let's grab our addition rule, and we get these 2 expressions. And they're like, equivalent expressions that we can use, drawn from the Venn diagram to help us relate the probability of all the regions, these 4 regions together. Okay, now because we've got mutually exclusive events between the yellow region and the green region, there's no actual overlap between the yellow region and green region. they're next to each other, but they're not crossing, because so they don't occur at the same time. So the intersection is 0, and that's why we've only got one bit plus the second bit, and we're not subtracting the intersection between the two. The intersection, probability of the intersection is 0. Now some other relationships we can come up with is, well, let's kind of say something for the sample space, everything all together. Well, it's like having the outside region, that's all this stuff, and then we union that together, we join it together with the two circles, A and B, joined together. So A and B together is A or B. Okay? Now, I've got two events that are unioned, so that if I'm interested in the probability of them, I've got to use my addition rule again. So probability of sample space is 1, which is easy. Now, I've got the probability of each added together using my addition rule. And again, they're not overlapping. My outside green shaded region is not overlapping my two circles. They're just next to each other. And so the intersection between them is 0. But hang on, I'm going to expand it a little further. I've got this guy here, which is probability of A or B, A union B, which I again use my addition rule to break it down into probability of A plus probability of B minus probability of their intersect. And we've got this nice, really big expression, and it equals to 1. Cool. What's that? That's not right. What should that be? Should be the intersect. So let's fix that up. Intersect. Good. Okay. Now, we can come up with other different expressions relating to the probabilities of all these different regions, and it's about learning how to use the multiplication rule, the addition rule, and combine them together to form expressions. We do that when we're required to do so. Okay, let's try this. Two interesting exam questions. The independent events pops up regularly, often as multiple choice questions, and the fundamental thing we're applying there for independent events is probability of A intersect with B. G'day. We've got a visitor. And we're back. So we're looking at this problem about independent events. We have this expression for independent events. The probability of the intersect of two events is simple multiplication of their respective probabilities. Okay. Now, but drawing on that idea, I first form this expression. Now that there is drawn on the information given to us. Probability of A intersect B is equal to P. So, using independent rule, I express it like this. And then I might be interested in how is probability of A and probability of B, how are they made up? What other expression are they equivalent to? How can I draw on my other information that's given to me, such as this one and this one? How can I draw on that and build it into these two? Well, by studying the Venn diagram previously, we saw that our whole event, A, is split up into two parts. A intersect B naught, and the green bit, A intersect B. And so the probability of an event like A is given by this right-hand side. And this is very useful because we have information about that in our question. So I form these two expressions, double brackets, because I've got two terms in each part pertaining to each product. Probability of A is equivalent to this. Probability of B is equivalent to the second part. That's B. And that's A. Keep going. Now I draw on the information from each part there, and I express now my expression all in terms of P. And I've got an equation which is a quadratic equation that I'm going to solve for P. And the solution on the CAS will give me this. P is equal to 0, or P is equal to 3 over 8. Now, I have two possibilities there. It pertains to this one, or it pertains to this one. I have to decide on which is the most correct answer. What do you think? Well, intuitively, I think some value here, 3 over 8, is more correct. Why? Well, if I come back to my expression here, and this one, then if I consider P having a value of 0, then I will have probability of not A intersect B is equal to, if that is a 0 there, equal to negative an eighth. And that doesn't seem right because you can't have negative probability. So that value doesn't seem to fit. It must be P is equal to 3 on 8 as the correct value. Alright, let's consider the next problem. So we have now, reposition stuff. Okay, for two events, probability P and Q, we've got probability of P intersect Q equals probability of not P intersect Q. So that's an interesting thing. What does that mean? Here, if we look at a Venn diagram, it's equivalent to have our region here, the blue region, as 1, with our green region here all equaling the same probability, meaning the same size. How can they be the same thing? Could it be that this intersection region will be the same if the whole of B is the same as A? Probability of A is equal to probability of B? Or in this case, in terms of P's and Q's, although it doesn't seem to be there, let's have a look at a way we can make sense of it. So, solution is, first off, that's the information given to us. Now, we're told that the events are independent. So, drawing on the definition of independence, probability of P intersect Q is given by probability of P times probability of Q. Now, on my right hand side, I have this expression, probability of P intersect Q. Now, it becomes this. Where did that come from? Again, think about my Venn diagram and how I can express it in a different way. So, by drawing on one of these rules and transposing that in terms of P's and Q's, I have this, right hand side. Next, I have this probability of the intersect P and Q, which, because they're independent events, can be expressed like this. And I've got two common terms there. This one and this one, so I can add it to the other side and I have 2 probability of P times probability of Q is equal to probability of Q. Cancel out my probabilities of Q and I'll end up with P is a half. Okay, so this is 2 important examples on how we are going to make use of the properties of independent events and regions of the Venn diagram and how we combine them to form expressions and how they all play out together in these types of problems. All right. Another important thing to consider with our probability is some other graphical representations. We looked at Venn diagram. How does that translate to our Karnaugh map? Okay, so we've got our 4 regions, 1, 2, 3, and 4, are all in the center where they cross. If we take any 2 events, probability of A and B, then we can lay out all the possibilities in this manner. And this is the general structure of our Karnaugh map. Okay, what's important to realize is that all the rows and columns must add to get to the outside number. So that means that I have this probability of event plus this one has to equal, they combine and add together to equal probability of A. And so on. I can take the same row, I can now add the rows. That plus that must equal probability of B. Okay? Let's look at a problem. Now, what we'll do is break it down this way. Alright, so let's consider, particularly in university, the probability that an art student studies a language is 0.3 and studying literacy is 0.6, and studying both language and literacy is 0.25. What is the probability that a student studies either language or literacy, or a student studies neither language nor literacy? Interesting. So some key words there that pop up is or, and this expression neither nor, it's kind of, if we break down the language, it's like using the keyword of not, which pertains to the complement, and the keyword or, which pertains to the union between 2 events. So first point is to consider how this information can be broken down into a Karnaugh map. Now, all the points given to us in the black is the information given to us in the problem. So, student studies language is probability of A. A is the study of language. And we also have an art student studies literature, which is studying literature is B, 0.6. Probability of B is 0.6. And studying both A and B, the intersection of A and B, is 0.25. So there's information. Now I'm going to add my columns and my rows to get the rest of the information. So 0.25 plus 0.35 gives me my 0.6, and 0.25 plus 0.05 gives me 0.3, and so on. And I can keep adding the rows and columns to complete my table. Now, having that laid out, all my information is there, I now need to just draw on it and read from it to answer some questions. So, answer question 1. The student studies either a language or literature. So that is probability of A or B, A union with B. And that is an addition rule of probability. So take the rule out, probability of A plus probability of B minus their intercept. And all the information is there in the table. and I can produce our result. Probability of B. Let's look at part B here. So it is about a student studies neither language nor literature. So what does that involve? Well, not language or not literature is another way of interpreting it. Okay? That was Cameron I just waved to. So we identify those values in the table, not A and not B. Not A is 0.7, not B is 0.4, so that's the two. Then we subtract their intersect, not A and not B, 0.35, and we get our result. What do you reckon? Easy, yeah? Good. So tree diagrams, also very fundamental and useful graphical representation for probability. And we want to use them particularly when we have conditional probability, or we have independent events as well, which is, in a sense, unconditional probability. So let's consider what it looks like for if we've got events that are independent of each other. So that means probability of B given A is just probability of B, does not depend on the outcomes of event A. And the intersection rule holds true for this as well. So let's flip 3 coins. 1, 2, 3. What kind of outcomes could we get? Well, one example of an outcome could be 3 heads. Head, head, head. Okay? We can lay out all the possibilities in tree diagram. So let's have a look what we have here. We've got 3 flips of a coin, so there's 3 parts to the tree. 1, 2, and then 3. And we can trace paths and get desired outcomes. So what we can notice here is, in a sense, probability of 3 tails is probability of 1 tail multiplied by the probability of another tail multiplied by the probability of another tail. Tail cubed, they're all the same probabilities, so we get 1/8. And in fact, we'll find that they're all probability of 1/8. In this one, we've got tail first, and then head second, and then tail third. And this is just a convenient notation to note down the outcomes we get all together. And again, 1/8. Okay? So what happens now for a different scenario where we've got conditional probability? Let's consider where the intersect of the 2 events is given by this condition on B given that A has occurred. So we looked at previously choosing socks randomly, and from a draw, if we've got different number of socks of particular colours, and if we were to choose one and then don't put it back, we keep it and then choose another one. Okay, that's without replacement. What will our tree diagram look like? So from the tree diagram, we could consider the probability of drawing 2 red socks. Well, that is probability of red 1 intersect red 2, or probability of red 1 and red 2. Drawing on our rule, I've got this first conditional factor multiplied by the probability of red sock. So if I draw out a red sock, I get 4 out of 6, because there's 6 socks in total, 4 of them are red. Now, if that is gone, I've got 5 socks left in the draw, but 3 of them are red. So 3 out of 5 for the conditional factor, probability of red 2, given that red 1 has occurred first. Okay, so we need to be able to consider what is left over in the sample space after we take one away, and how many of the outcomes we have. Let's try this one. What's the probability of red 1 first, and then a white sock second? So that might be written as probability of white 2 given red 1 has occurred times probability of red. Alright, so if a red sock is drawn first, then that's 4 out of 6 probability. But then having red 1 drawn out, I've got now 5 socks left in the drawer. How many of them are white? I've still got my full 2 white pairs. So it's a 2 out of 5 left. And that gives us a result of 8 out of 30. And that simplifies nicely, being 4 out of 15. So let's look at a more focused question. What is the probability of drawing 1 white pair of socks? Well, we can get 1 pair of white socks in 2 ways. Could happen with white was picked first, and then any other color like red. And then what about if red was picked first and then white was picked second? There are 2 scenarios, one or the other, and for probabilities of those events we're going to use the addition rule. So I get this expression down the bottom that allows me to find probability of just one thing. Okay? Yep. That is also drawn from the Venn diagram expressions that we came up previously. So I've got one of them produced. Let's get the other one. Probability of white first and red second. Well, white first is, we've got 2 white pairs out of 6. And then we've got 4 reds out of 5, which is an 8 out of 30. 4 out of 15. And so what we would end up then is probability of white is adding those 2 together. One plus the other, and it'll give you an 8 out of 15. Okay? Alright. Here's an important problem. This one pops up quite often. This one you can draw on a graphical representation, like a tree diagram, but it's not necessary, because as long as we understand the relationships between conditional probability and the intersection of events and draw on those rules, we're able to solve it. So the chance that a harvest is poor than average is 0.5, but if it is known that a certain disease is present, this probability increases to 0.8. So this good harvest or poor harvest is dependent on whether disease is present. So you can already see some condition occurring there. The disease D is present in 30% of the harvest. Find the probability that when the harvest is observed to be poorer than average, the disease is present. So the first thing we're going to do is identify the key information and just summarize it in the right notation on the side. So from here, harvest is poorer than average is 0.5. So that's an important piece there. Okay, but if it is known that a certain disease is present, this probability increases to 0.8. So there's a conditional part there. And the disease is present 30% of the time of the harvests. So considering that, I can summarize it in this manner. what we're after is the probability that when the harvest is observed to be poorer than average, the disease is present. That is, disease given harvest. Okay, D given H. How does that work out? We need a relationship between maybe probability of D given H and this information that's given to us, probability of H given D. Are they the same if they're backwards? Maybe not. Let's look at the breakdown on a tree diagram. Okay, if we consider the disease is present first, and then we can get the chance of a poor harvest or not a poor harvest, depending on whether the disease is present. We can lay out some information in the tree diagram, but what we're truly interested in is how can probability of D given H relate to probability of H given D? Are they the same thing? Not necessarily. We're going to use our multiplication rule because this is the rule that has the conditional probability terms factors in it. So there's one representation using the multiplication rule. By transposing for the conditional probability part, I can write it like this. Now I can see that my intersection, D intersect H, I can also write it in this manner. Okay, just by reversing the order of my event that's given, and now multiply by probability of D for when the condition is dependent on whether we have a poor harvest or not. And I can put it all together in one expression. Now I've got all parts available in the given information and I can get a result. Okay, now here's a classic example that we have worked on, started to work on in class. Let's see if we can get some information about this one. A bag contains 3 red, 4 white and 5 black balls. If 3 balls are taken without replacement, so this term without replacement, which means we take the ball and we don't put it back in the bag, in the container. What is the probability that they are all the same colour? Okay, so all the same colour would be something like a red first drawn, red second drawn, red third drawn, or white first, white second, white third, or black first, black second, black third. There are no other possibilities there. Okay, so we're interested in determining probabilities of each. Well, the first one, if I'm taking the probability of all this together, this is what I'm interested in, then as you can see I've got some intersection of events there, or pertains to the union. So where I have the union of events, I am in a sense using my addition rule, adding them all up. So this would be the same as probability of red 1, red 2, red 3 plus probability of white 1, white 2, white 3 plus probability of B1, B2 and B3. Bananas. No, not bananas, black balls. Okay, so we are interested in working out each separately, and given the fact that they are conditional to each other, we have to think about the problem logically. As we take one ball out, how many are left in the sample space? So drawing on our idea of the multiplication rule now, I'm going to have the products of these three together. But I'm going to start with the probability of the third red. But that depends on the outcomes of the second draw, of red 2 being drawn. Multiplied by what's given, R2. But R2 depends on R1. Then I have to multiply by what's given, R1. Okay? So there's a way, that's the how we would formulate the multiplication of these rules for 3 events occurring. The same approach applies for white. And it happens for both white and black balls, and we can have all the expression written in this form. We now want to determine what are the probabilities of each of the factors. So we have probability of red 3 given red 2. Well, we have to count now how many we have. We've got 3 red, 4 white, 5 black. So altogether there are 12 balls. So the number in my sample space is equal to 12. Okay? So what we have is, on the first draw, we have 3 out of 12. And then when we don't replace, we've got 1 less. So we'll have 2 more reds out of 11. And on the third draw, we've only got 1 red ball left, but 10 left balls in the bag. Plus, now for the white balls, at first we've got 12, and we've got 4 to start off with. Then after the first draw, we'll have 11 left in the bag, and 3 of them are white. And then on the third draw, we've got 10 left in the bag, and 2 of them are white. And then for the black balls, first we start off with 12 balls, and there are 5 of them black. Then we've got 4 out of 11 black in the second, and then 3 out of 10 in the third. Get the idea? And we whip it all up nicely on CAS, hit enter, and we get our result of 3/44.
You got me.
Myself.